Welcome to Modern Day Applications of Fractals, prepared by Rebecca Amon, Jameson Willant, Andrew Stefano, and Brenda Ventura. Fractals are a very large part of our modern world, and it seems they are more the norm than the exception when you know what to look for. Our team has explored a few of these: fractals in bridges and cables, fractals in our Earth, fractals in cities, and fractals in art. We hope you enjoy learning as much as we enjoyed creating. Fractal ideas with regards to building bridges have been used by people for centuries in the engineering of super strong cables. Long before we built the Golden Gate Bridge, the Inca in South America were building bridges across mountainous ravines that were hundreds of feet wide. The cables in these bridges were woven by hand out of long strands of stiff Goya grass. Just as in a modern steel cable, a small number of fibers are woven into a large fiber, several of which are then woven into a larger rope. This repetitive fractal pattern provides great strength and allows a very long cable to be woven from thousands of individual pieces of grass, no longer than a meter or two each. Cable technology is essential for building suspension bridges. The Inca weavers and the modern steel cable makers both use a repetitive process to create strong fractal cable patterns. A steel cable is formed from a bundle of smaller cables, which themselves are formed of smaller bundles. This picture shows the repetitive fractal pattern, but it does not show you the various strands, ropes, and cables that were all wrapped to spiral around each other. This greatly increases the total strength of the cable. The concept of fractals has also been adopted in the field of earthquake engineering. The transverse responses of cable-stayed bridges and the fractal properties are also analyzed. Here is a cutaway schematic showing the possible configurations of a steel cable bundling in cross-section. You'll notice the core with the fractals around the outside, and then the binding together of all of the factors of the cable. Fractal ideas with regard to building bridges have been used by people for centuries in the engineering of super strong cables. Long before we built the Golden Gate Bridge, a fractal is a natural phenomenon or a mathematical set that exhibits a repeating pattern that displays at every scale. It is also known as expanding symmetry or evolving symmetry. Here you will find examples of bridges and cable fractals. Helge von Koch was the Swedish mathematician who came up with the geometric fractal process known as the Koch snowflake and the Koch curve. It's a geometric equation where the same set of rules is repeated infinitely. The interesting thing about this process is that you can take a finite object, like the coastline of a country, and find that it can have an infinite length of perimeter when attempting to measure it. Here you can see an example of the Koch curve. Here you can imagine that the Koch snowflake is an island in the middle of the ocean. If this were the case, the Koch curve would be the coastline. The island is a small landmass in the middle of the ocean, yet has an infinitely long coastline. Let's look at this principle in a real-life example. Here is a map of the United Kingdom. The white box at the bottom left of the island is outlining the town of Lower Boscaswell on the western edge of England. This is an example of where we will see the Koch curve rule appear as we zoom in further and further to look at the coastline. Here you can start to see how the edge of the coastline is starting to look like the edge of the Koch curve in the previous slide. Here you can start to see how the edge of the coastline is starting to look like the edge of the Koch curve in the previous slide. In this slide, the edge of the coastline is becoming more detailed, and you can see that the edge of the land isn't so smooth. In this slide, the edge of the coastline is becoming more detailed, and you can see that the edge of the land isn't so smooth. Here we see even more detail as we zoom in further. Here we see even more detail as we zoom in further. Our last slide of Lower Boscaswell shows us that the island of the UK is really a great example of a Koch snowflake. Next time you're looking at a map, or even an activity just for fun, zoom in on a coastline and see if the Koch curve appears as a fractal in nature for you. Our last slide of Lower Boscaswell shows us that the island of the UK is really a great example of a Koch snowflake. Next time you're looking at a map, or even an activity just for fun, zoom in on a coastline and see if the Koch curve appears as a fractal in nature for you. The rules of chaos theory and fractals apply directly to the evolution of cities, and the study of urban pattern allows us to benefit from the experiments of past cultures to shape our own future with as much awareness of the consequences of our actions as possible. A large fractal city tends to grow that way by absorbing lots of smaller villages. So the city becomes a collection of villages, and the villages are collections of neighborhoods. The roads in a fractal city tend to go in seemingly haphazard directions, but really they serve as direct connections between various central hubs in a dynamic urban network. Once a city forms a shape, there are often negative feedback loops that serve to stabilize its shape. Sometimes, with certain rule systems in place, the cities take on fractal characteristics. This is particularly common in medieval cities in Europe and in the Middle East. This is an example of Celtic fractal art from 597 AD from the Book of Kells. The illustrations and calligraphy almost identically mirror modern fractals explained by Mandelbrot. These patterns show up in many different cultures at different times in history before the 1980s. These also represent ancient depictions of fractal art. Upper left is from an Ethiopian ornament portraying the fractal designs. In the middle on the top is an example of Italian Renaissance art of the Da Vinci's era. The top right is Persian and Islamic art, mostly found in rugs and hangings. And below is the Hindu depictions of infinity. Versions of these are mirrored in Egyptian, Islamic, and Judaic religious symbols also. Fractals existed in art before they were explained, but why do our brains replicate and recognize these representations? It is said when Mandelbrot first looked upon the equations and their results, they seemed quite strange, but after studying them a while, they became comfortable, even familiar. It is quite possible our brains might even be hardwired to understand and embrace these patterns, which seems plausible looking at these ancient pieces of what we would now consider fractal art. Well, maybe not discovered, but finally put into words. He explained them as being geometric shapes that when divided into parts, each part would be a smaller replica of the whole shape. He came up with the term fractal as the new scientific term for this mathematical expression. With the advent of computers, the formulas that used to take mathematicians thousands of hours took only a few minutes, and even more infinite variations were made possible. It's amazing what can be created from one simple formula, but that seems to be the beauty of fractals, a simple formula for a complex solution. What is the future of fractals? There is a program called, ironically, the Mandelbulb that creates 3D fractal images, which is the first step in the process of 3D printing. Right now, these 3D printers, once used for entertainment, are being put to use creating food, tools, building materials, and are even being tested with human cells with a look towards creating organs that can be implanted. Art imitating life, literally. What is the future of fractals? There is a program called, ironically, Mandelbulb that creates 3D fractal images, which is the first step in the process of 3D printing. Right now, these 3D printers, once used for entertainment, are being put to use creating food, tools, building materials, and are even being tested with human cells with a look towards creating organs that can be implanted. Art imitating life, literally. We hope you've enjoyed our presentation on fractals in the modern world. We'll leave you with the last quote by Mandelbrot. I've found myself in the position of that child in a story who notices a bit of string and, out of curiosity, pulled on it to discover that it was just the tip of a very long and increasingly thick string, and kept bringing out wonders beyond reckoning. Thank you very much.